ಹಲೋ ಸ್ಟೂಡೆಂಟ್ಸ್, ಇವತ್ತು ನಾವು IC LM2576 ಅಂದರೆ ಏನು, ಇದು ಏನು ಕೆಲಸ ಮಾಡ್ತದೆ, ಇದನ್ನು ಎಲ್ಲಿ ಯೂಸ್ ಮಾಡ್ತಾರೆ, ಇದರ ಉಪಯೋಗ ನಮಗೆ ಯಾವ ರೀತಿ ಎಲೆಕ್ಟ್ರಾನಿಕ್ಸ್ನಲ್ಲಿ ಎಲ್ಲಿ ನಮಗೆ ಸಿಗ್ತದೆ ಅನ್ನೋದನ್ನು ನಾವು ನೋಡೋಣ. LM2576 ಈಸ್ ಎ ಸ್ವಿಚ್ ಮೋಡ್ ಸ್ಟೆಪ್ ಡೌನ್ ವೋಲ್ಟೇಜ್ ರೆಗ್ಯುಲೇಟರ್ ಅಂತ ಹೇಳ್ತೀವಿ. ದ ಮೀನಿಂಗ್ ಆಫ್ ಸ್ವಿಚ್ ಮೋಡ್ ಸ್ಟೆಪ್ ಡೌನ್ ವೋಲ್ಟೇಜ್ ರೆಗ್ಯುಲೇಟರ್ ಅಥವಾ ಇದನ್ನು ಬಕ್ ಕನ್ವರ್ಟರ್ ಅಂತ ಕೂಡ ಕರೀತಾರೆ. ಹಾಗಾಗಿ ಇದು ಯಾವ ಸಬ್ಜೆಕ್ಟಲ್ಲಿ ಬರ್ತದೆ ಅಂತೇಳಿದ್ರೆ, ಯಾವ ಟಾಪಿಕಲ್ಲಿ ಬರ್ತದೆ ಅಂತೇಳಿದ್ರೆ SMP ಅನ್ನೋ ಟಾಪಿಕ್ನಲ್ಲಿ ಇದು ಬರ್ತದೆ. SMP ಅಂದರೆ ಏನು? ಸ್ವಿಚ್ ಮೋಡ್ ಪವರ್ ಸಪ್ಲೈ. ಇದು ಪವರ್ ಸಪ್ಲೈಗೆ ಸಂಬಂಧಿಸಿದಂಥ ಒಂದು ಟಾಪಿಕ್. ಇಲ್ಲಿ ನಾವು ಪವರ್ ಸಪ್ಲೈ ಅಂದ ತಕ್ಷಣ ನಮಗೆ ಎರಡು ರೀತಿಯ ಪವರ್ ಸಪ್ಲೈಸ್ ಬರುತ್ತೆ. ಒಂದು ಲೀನಿಯರ್ ಪವರ್ ಸಪ್ಲೈ, ಇನ್ನೊಂದು ಸ್ವಿಚ್ ಮೋಡ್ ಪವರ್ ಸಪ್ಲೈ, ಸ್ವಿಚಿಂಗ್ ಪವರ್ ಸಪ್ಲೈ ಅಂತ ಕೂಡ ಕರಿತೀವಿ. ಲೀನಿಯರ್ ಪವರ್ ಸಪ್ಲೈನಲ್ಲಿ ನಾವು ಮಾಮೂಲಾಗಿ ಹಾಫ್ ವೇವ್ ರೆಕ್ಟಿಫೈರು, ಫುಲ್ ವೇವ್ ರೆಕ್ಟಿಫೈರು, ಬ್ರಿಡ್ಜ್ ವೇವ್ ರೆಕ್ಟಿಫೈರ್ಸನ್ನು ಬಳಸ್ಕೊಂಡು IC 7805 ಅಥವಾ 7809 ಅಥವಾ 7812 ಈ ಥರ ರೆಗ್ಯುಲೇಟರ್ಸ್, IC ರೆಗ್ಯುಲೇಟರ್ಸನ್ನು ಯೂಸ್ ಮಾಡಿಕೊಂಡು ನಾವು ಅನ್ರೆಗ್ಯುಲೇಟೆಡ್ ಪವರ್ ಸಪ್ಲೈಯನ್ನು ಪವರ್ ಸಪ್ಲೈ ಆಗಿ ನಾವು ಕನ್ವರ್ಟ್ ಮಾಡೋದು ನಮಗೆ ಗೊತ್ತಿದೆ. ಸೊ ಅದಕ್ಕೂ ಈ ಸ್ವಿಚಿಂಗ್ ರೆಗ್ಯುಲೇಟರ್ಸ್ಗೂ ಏನಪ್ಪ ವ್ಯತ್ಯಾಸ ಅಂತ ಹೇಳಿದರೆ, ಅನ್ರೆಗ್ಯುಲೇಟೆಡ್ ಪವರ್ ಸಪ್ಲೈಯಿಂದ ನಾವು ಲೀನಿಯರ್ ರೆಗ್ಯುಲೇಷನ್ ತಗೊಂಡಾಗ ಆ ಒಂದು ವೋಲ್ಟೇಜಸ್ಸಲ್ಲಿ ಏನಾಗುತ್ತೆ, ಡಿವೈಸಸ್ಸು ಹೀಟ್ ಆಗ್ತದೆ. ಲೋಡಿಂಗ್ ಜಾಸ್ತಿ ತೊಗೊಂಡಾಗ, ಕರೆಂಟ್ ಲೋಡಿಂಗ್ ಜಾಸ್ತಿ, ಔಟ್ಪುಟ್ಟಲ್ಲಿ ಕರೆಂಟ್ ಲೋಡಿಂಗ್ ತೊಗೊಂಡಾಗ ಹೀಟ್ ಆಗ್ತದೆ ಇವು. ಆವಾಗ ನಾವು ಆ ರೆಗ್ಯುಲೇಟರ್ಸ್ಗೆ ಹೀಟ್ ಸಿಂಕ್ಸನ್ನು ನಾವು ಬಳಸ್ಕೊಳ್ತೀವಿ. ಅದು ಜಾಸ್ತಿ ಹೀಟ್ ಸಿಂಕ್ ಇಲ್ಲ ಅಂತೇಳಿದ್ರೆ ಡಿವೈಸಸ್ಸು ಡ್ಯಾಮೇಜ್ ಆಗುತ್ತೆ. ಆ ಒಂದು ಡಿಸಡ್ವಾಂಟೇಜನ್ನು ಈ ಸ್ವಿಚಿಂಗ್ ರೆಗ್ಯುಲೇಟರ್ಸು ಓವರ್ಕಮ್ ಮಾಡುತ್ತೆ. ಅಂದರೆ ಅದರ ಒಂದು ಡಿಸಡ್ವಾಂಟೇಜಸನ್ನು ಅಡ್ವಾಂಟೇಜಸ್ ಆಗಿ ಇದು ನಮಗೆ ಪರಿವರ್ತನೆ ಮಾಡ್ತದೆ. ಈ ಸ್ವಿಚಿಂಗ್ ರೆಗ್ಯುಲೇಟರ್ಸ್ನಲ್ಲಿ ನಾವು ಈ ಸ್ವಿಚಿಂಗ್ ರೆಗ್ಯುಲೇಟರ್ ICಸನ್ನು ಬಳಸ್ಕೊಂಡು ನಾವು ಸ್ವಿಚಿಂಗ್ ರೆಗ್ಯುಲೇಷನ್ಸನ್ನು ನಾವು ತಗೊಳ್ತೀವಿ. ಇಲ್ಲಿ ಕ್ಲೀನಾಗಿ ಹೇಳಿದ್ದಾನೆ, LM2576 is a switch mode step down voltage regulator that can provide a fixed output voltage. Its output voltage can also be adjusted in a range of 1.23 volts to 37 volts by connecting external components. This IC is very simple to use, and this feature makes it ideal for a wide range of applications. It has built-in fault protection against overcurrents, voltages and temperatures. ಈ IC 2576 ಪಿನ್ಔಟ್ ಡಯಾಗ್ರಾಮ್ ಇದು ಹೇಗಿದೆ ಅಂತ ನೋಡೋಣ. ಇಲ್ಲಿ ನಮಗೆ ಈ ಪಿನ್ ಡಯಾಗ್ರಾಮ್ ಕೊಟ್ಟಿದ್ದಾರೆ. ಇದು IC ಅಂದ ತಕ್ಷಣ ನಮಗೆ ಪಿನ್ ಡಯಾಗ್ರಾಮ್ ಇರುತ್ತೆ. ಪ್ರತಿ ICಗೂ ಪಿನ್ ಡಯಾಗ್ರಾಮ್ ಇರುತ್ತೆ, ಪ್ಯಾಕೇಜ್ ಇರುತ್ತೆ, ಲೀಡ್ ಕಾನ್ಫಿಗರೇಷನ್ ಇರುತ್ತೆ. LM2576 ಪಿನ್ಔಟ್ ಡಯಾಗ್ರಾಮ್ನಲ್ಲಿ ಇದು ನಮಗೆ 5 ಲೀಡ್ IC ಅಂತ ಕರಿತೀವಿ. 5 ಲೀಡ್, ಇದಕ್ಕೆ 5 ಲೀಡ್ಸ್ ಇರುತ್ತೆ. ಇದು ನಮಗೆ T0220 ಪ್ಯಾಕೇಜಲ್ಲಿ ನಮಗೆ ಅವೈಲಬಿಲಿಟಿ ಇರ್ತದೆ. ಈ 5 ಲೀಡ್ಸು ಸ್ಟ್ರೈಟ್ ಲೀಡ್ಸ್ ಆಗಿ ನಮಗೆ ಸಿಗ್ತದೆ. ಇಲ್ಲಿ ಅದನ್ನು ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಿದ್ದಾನೆ ಕ್ಲೀನಾಗೆ. ದಿಸ್ ಪಿಕ್ಚರ್ ಶೋಸ್ a pinout diagram of LM2576 buck voltage regulator. It works either in fixed voltage or in adjustable voltage mode. For details of each pin, refer the next session. It is explained. It is having 5 pins. Here in the pin identification part, the dot represents pin number 1. Second one, third, fourth and fifth, it is given by words pin number first is V in, pin number 2 it represents output, pin number 3 it is connected to ground, pin number 4 it is connected to feedback network, pin number 5 it is connected to on off points. So in this pin configuration it is explained. It is important to know the description of pins of IC before using it. The functions of all the pins of LM2576 are explained below. ಇದನ್ನು ಇಲ್ಲಿ ಹೇಳ್ತಾರೆ. ಪಿನ್ ನಂಬರ್ 1 ಏನು ಕೆಲಸ ಮಾಡ್ತದೆ? It is input pin where a signal to be regulated is applied. Pin number 2, it is an output pin. This pin is used to obtain the regulated signal output. Pin number 3, it is ground. The ground pin is connected to the ground of the circuit. Pin number 4, it is feedback. The feedback is an input pin used to set output voltage in case of adjustable output. To adjust the output voltage, it is connected to the midpoint of the feedback divider network. In case of fixed output, connect this pin to the capacitor. Pin number 5, it is given by on off. It is enable input pin. This pin should not be left unconnected. Connect it to the ground to enable the voltage regulator. To disable the regulator, connect this pin to high logic. So these are the pin details of IC LM2576. It is this IC switching regulator LM2576 IC is named by switching regulator. It is having some features. What are those features here we have to follow? It is a fixed voltage frequency regulator having an internal oscillator frequency of 52 kHz. Input voltage can be applied up to 40 volts and up to 60 volts for HV versions, high voltage versions. This regulator can provide fixed output voltages of 3.3 volts, 5 volts, 12 volts and 15 volts. The output voltage can be varied from 1.23 volts to 37 volts by connecting external components. It can withstand a tolerance of plus or minus 4% on output voltage when the input voltage is in the range specified and output load conditions are satisfied, and a tolerance of plus or minus 10% on the oscillator frequency. Here its output current is specified up to 3 ampere. Protection circuitry includes thermal shutdown and current limit protection. It has an under voltage lockout circuit which keeps the input voltage in a range and keeps regulator off until it comes to a certain threshold level. So this is the fundamental details over the IC LM2576, which is called as the switching regulator or step down buck regulator used in SMPS. So here one more important, where to use 3 ampere step down voltage regulator. LM2576 is a 3 ampere voltage regulator that provides an excellent line and load regulation. It is suitable for driving 3 ampere loads. Due to its convenient use, it is also used as a step down switching regulator. It can use readily available inductors. This feature makes it ideal for designing switch mode power supply as it greatly simplifies their design. So if you are looking for a linear buck voltage regulator that can drive 3 ampere load and provide an output in the range of 1.323 volts to 37 volts with an efficiency of 88%, then you can use this IC as a voltage regulator. LM2576. switching regulator. So how to use this LM2576? The use of this chip is explained through the circuit that is given below here. The circuit is given here explained. So in this session we will see examples of how to use LM2576 in fixed voltage and adjustable voltage mode. So fixed voltage mode, here is a circuit. It defines the fixed voltage regulator example. This circuit is for a fixed voltage regulator which takes an unregulated DC voltage at its pin number 1 and then converts it into plus 5 volts regulated voltage which is obtained from pin number 2. An output capacitor is required for stability. The output capacitor acts as a filter and removes ripples from the output voltage. It also provides loop stability. A Schottky diode 1N5822 that connects across an output pin and L1 inductor. When regulator internal switch is off, it offers a path for inductor current. For normal operation, you should connect on-off pin to the ground terminal. Before selecting a Schottky diode, you should make sure that the rating of this diode is 1.2 times greater than the load current requirement or output current. So that is for a fixed voltage regulator example circuit. Next, adjustable voltage power supply circuit. Here is an example for adjustable voltage power supply circuit example. To adjust the output voltage, two resistors R1 and R2 are connected, which constitute a feedback network. The output voltage or the values of resistors can be calculated by keeping the two values constant and put them in the following equation to find third value. V out is equal to V reference into 1 plus R2 by R1, where V reference is equal to 1.23 volts. So here some calculations needed for adjustable voltage power supply requirements. Applications where this LM2576 switching regulator are used. It is an important. The LM2576 is a high efficiency buck regulator which is used in large variety of applications that includes designing of SMPS. It is an efficient pre-regulator for designing linear regulators. These are on-card switching regulators. It can also be used to convert a positive input voltage to negative output voltage. ಸೊ ಇದು ನಮಗೆ LM2576 ಸ್ವಿಚಿಂಗ್ ರೆಗ್ಯುಲೇಟರ್ ಬಗ್ಗೆ ನಮಗೆ ಇರುವಂಥ ಒಂದು ಮಾಹಿತಿ. ಇದನ್ನು ಸ್ವಲ್ಪ ಇದಕ್ಕೆ ಒಂದು ವಿಡಿಯೋ ಇದೆ. ಆ ವಿಡಿಯೋದಲ್ಲಿ ನಮಗೆ ಚೆನ್ನಾಗಿ ಹೇಳಿದ್ದಾರೆ, SMPS ಅಂದರೆ ಏನು ಅಂತೇಳಿ ಚೆನ್ನಾಗಿ ಹೇಳಿದ್ದಾರೆ. ಅದನ್ನು ನೀವು ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳೋದಕ್ಕೆ ಪ್ರಯತ್ನ ಮಾಡಿ. ಅದನ್ನು ನೋಡೋಣ ಈಗ.
Switch mode power supplies are everywhere. For DIY electronics projects, you will come across modules like these ones that promise high efficiency and a wide input voltage range. They are also present in AC mains equipment like phone chargers, computer power supplies, and even inside regular electronic gadgets. While they might appear to be very complicated at first glance, their basic operation is actually pretty simple. But why are they so popular and how do they work? That is what we are going to find out in this video. Towards the end, we will also take a look at the power supply present in a Wi-Fi bulb so that you can see how it is all put together in commercial products. Let's start with the main voltage regulator ICs themselves. The most common one being the 7805 for the linear regulator and the LM2576 for the switch mode regulator. Keep in mind that you do have many other voltage regulators as well, and while they do have their own variations, the principles that we will be covering in this video are applicable to them as well. In an earlier video on linear power supplies, we saw that a linear regulator like the 7805 is used to provide a steady output voltage from the rectified and filtered DC input. Here's how it works. We start with the pins themselves. A linear voltage regulators generally have a total of 3 pins: input, output, and reference ground. Internally, you have something called an op-amp, a transistor, a feedback circuit, along with the reference voltage. The output of the op-amp will be the difference between the reference voltage, which is a constant, and the output of the feedback circuit, which depends on the final output voltage. The op-amp output will be an analog voltage which will control the transistor. The circuit is tuned such that the output voltage will be a constant, 5 volts in the case of the 7805 regulator. If the input voltage rises, then feedback from the output will be high initially. This will cause the op-amp output to change such that the output voltage will be lowered, thus regulating it. What we have here is a closed-loop system that constantly monitors the output voltage to control the transistor. The end result is a steady output voltage. For adjustable linear regulators like the LM317, the feedback resistors need to be supplied externally, and this allows you to adjust the output voltage. What we have here is a transistor, some form of feedback that is fed to an op-amp which controls the transistor. This setup is simple, but the main drawback is the heat generated by the transistor that is operating in the linear region. The heat generated rises as the input voltage increases and as the current flowing through it increases. Transistors are not very efficient when used in a linear region. To overcome this, they have to be used as a switch that is between their cutoff and saturation regions, and that is exactly what switching regulators do. Instead of operating the transistor in the linear region, we add an oscillator circuit that operates at a high frequency. To control the transistor, we use something called a comparator, which uses the output from the op-amp and the oscillator as the input. A comparator is just like an op-amp, but instead of giving us the analog difference between the two inputs, it compares the two and gives us a higher output whenever the positive input is higher than the negative input. You can think of it as a digital or binary version of the op-amp. The output from the comparator is used to rapidly switch the transistor between the cutoff and saturation regions. We will end up with an output that is going to be more like a square wave at the frequency of the oscillator. This means that we need to add a bit of filtering to smoothen it out. For this, we add an inductor along with a capacitor. They are both energy storage elements, with the capacitor resisting any changes in the voltage and the inductor resisting changes in the current flowing through it. We also add a diode to suppress any negative voltages and to also provide a path for the current to flow when the transistor is off. If we take a look at the LM2576, then you will see that it has a bunch of pins. We have the input, ground, and output along with the external filtering circuit. We then have the feedback pin, which is very critical for correct operation, followed by the on-off pin that can be used to shut off the regulator. The on-off pin is optional and is not required for the actual switching operation, so we will ignore it for now. These are the block diagrams it contains internally. The input voltage passes through a transistor to reach the output pin, and the transistor is driven by all these other blocks before it. It all starts at the feedback pin, where a voltage divider network is used to reduce the voltage to a safe value. This is then compared to a known reference, which is 1.23 volts in this case. The output from the op-amp will be the error, which is then fed into the comparator along with the oscillator output. This will give us a binary or digital signal that is then passed to the driver circuitry, which is used to meet the interfacing requirements for the final transistor. When the regulator is in the power down or off state, this logic gate will prevent the comparator output from reaching the driver, switching off the output. Similarly, the thermal and current monitoring circuitry is used to ensure safe operation. That's pretty much all that's happening in the DC to DC switching regulators. This particular chip is a step-down converter, which means that the output voltage will be lower than the input. However, similar principles apply to step-up converters whose output voltage is higher than the applied input voltage. Now that we know how the actual DC to DC conversion takes place inside a switching voltage regulator, we need to take a look at how the AC mains voltage power supplies work. The three main disadvantages of a linear power supply are its weight, physical size, and that most of them operate at a single mains voltage. To get them to work at different voltages, you will need to use an external voltage conversion device, which is nothing but an appropriate transformer. All of these three issues are due to the internal transformer that is being used within the power supply. The size of the transformer depends on several factors, the main being the size of the core, and this core size depends on the transformer operating frequency. A lower frequency like that of the AC mains will result in a higher core size. However, at frequencies of several kilohertz, the code dramatically decreases both physically and in terms of weight. Switch mode power supplies make use of such high frequency transformers. Once again, there are different ways by which they are constructed, so we will stick to the general approach in this video. Transformers cannot work on DC or steady voltages. They need some sort of AC or alternating voltage to work correctly. Our first task is to then somehow increase the frequency of the mains voltage. We can do that by first converting it to DC using a bridge rectifier, and then adding a filtering circuit to smoothen the output. We can then use an oscillator along with a transistor to chop this voltage and give us an alternating voltage whose frequency will depend on the oscillator frequency. We can then use a high frequency transformer to step this down to a lower voltage. Finally, we can add another filtering circuit to give us a stable DC output. The filtering stage tries to also eliminate the oscillator frequency from the output to give us a clean voltage. You will notice that the final section is identical to the linear power supply that we looked at previously. Adding these additional stages has eliminated the need for a bulky, low-frequency transformer, giving us a nice and compact power supply. Two things to note here. Firstly, some power supplies like these can also detect the input DC voltage. This allows them to work at a wide input voltage range, which is more common in modern power supplies. Secondly, the oscillator, transistor, voltage sensing and feedback blocks are generally handled by a single controller IC, and this helps simplify the circuit further. To give you an example, let's take a look at this smart LED bulb that I had taken apart long ago. You will notice that there are two main PCBs, one that contains all the different LEDs and the other that contains the power supply and Wi-Fi module itself. Before we proceed, I would like to mention that working with AC mains voltages can be very lethal. Switch mode power supplies like these are even more dangerous as they convert the AC mains voltage to a very high DC voltage. They also contain capacitors that can store these high voltages for extended periods of time. So please do not play around with these devices if you do not know what you are doing. The LED board contains several different LEDs as seen here, and it is linked to the main PCB through these pads. We do not care about the LED board in this video, so let's focus our attention to the main PCB. First, we have the Wi-Fi module that takes care of the main communication for us. We also have a bunch of other discrete components that will be used to interface the LEDs. The Wi-Fi module works at 3.3 volts, so the outputs from the module will also be at this low voltage. The discrete components will carry out some form of level conversion, and they will also handle the PWM signals which are needed to control the brightness. On the power supply side, we have the AC mains input that is directly connected to this chip here, which is a full bridge rectifier in a single package. This one is the ABS10 that contains all the 4 diodes internally, and the end result is that we save a bit of space by using something like this. The output from the bridge rectifier is then filtered using this capacitor, and that is why it has a high voltage rating of 400 volts. The next IC on the board is this one here, and that is the main switching controller that is responsible for most of the operation. This one has the markings YT5203 on it, but I couldn't find its datasheet, so here's another one to give you an idea what these are like. This one works at a frequency of 132 kHz, and it combines a high power MOSFET, oscillator, and other things in one little package. They have also provided a reference diagram which is useful. An optocoupler is used to provide feedback to the controller, which then switches the DC input voltage accordingly. The DC voltage is also applied to the high frequency transformer, whose output is then rectified and filtered. Going back to the circuit, we can see the high frequency transformer here, the output diode, and so on. You will notice that there is another chip on board, and this one is also a switching regulator, but it is the lower voltage kind, similar to the LM2576 that we looked at in the beginning of this video. I don't have the schematic to verify this, but I would suspect that the LEDs are being driven at a much higher voltage, and this is obtained directly from the main switcher IC. The smaller step-down converter will be used to generate the lower 3.3 volts that is required for the Wi-Fi module. As mentioned, there are different types available, but I hope this video has given you some understanding of the basic principle behind them.
ಈಗ ಅದು ಎಕ್ಸ್ಪ್ಲನೇಷನ್ನ ನೋಡಿದ್ರಲ್ಲ, ಅದರಲ್ಲಿ ಕ್ಲೀನಾಗೆ ಯಾವ ರೀತಿ ನಮಗೆ SMP ವರ್ಕ್ ಆಗುತ್ತೆ ಅಂಥೇಳಿ ಫ್ರಮ್ ಸ್ಟಾರ್ಟಿಂಗ್ನಿಂದ ಎಂಡಿಂಗ್ವರೆಗೂ ತುಂಬ ಚೆನ್ನಾಗಿ ಹೇಳಿದ್ದಾರೆ. ಅದನ್ನು ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳೋದಕ್ಕೆ ಟ್ರೈ ಮಾಡಿ. ಇದನ್ನು ನೀವು ತಿಳ್ಕೊಂಡ್ರೆ SMP ಇದು ಎವರ್ಗ್ರೀನ್ ನಾಲೆಡ್ಜ್ ಇದೆ. ಇದು SMP ನಮಗೆ ಯಾವತ್ತಿಗೂ ಕೂಡ ಅದು ವ್ಯಾಲ್ಯೂಬಲ್ ನಾಲೆಡ್ಜ್. ಅದು ಇದನ್ನು ಎಷ್ಟು ತಿಳ್ಕೊಳ್ಳೋದಕ್ಕೆ ತುಂಬ ಪ್ರಯತ್ನ ಮಾಡಿ. ಇದು ತಿಳ್ಕೊಂಡಷ್ಟು ನಿಮಗೆ ಒಳ್ಳೆಯದಾಗುತ್ತೆ, ಆಯಿತಾ. ಇದುವರೆಗೂ ನೀವು LM2576 ಈ IC ಬಗ್ಗೆ ನಾವು ನಿಮಗೆಲ್ಲ ಒಂದು ಫಂಡಮೆಂಟಲ್ ನಾಲೆಡ್ಜನ್ನು ಹೇಳಿದ್ದೀವಿ. ಸೊ ಇದನ್ನು ನೀವು ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳೋದಕ್ಕೆ ಪ್ರಯತ್ನ ಮಾಡಿ. ಇದು ಅರ್ಥ ಆಗಿದೆ ಅಂದ್ಕೊಳ್ತೀನಿ. ಥ್ಯಾಂಕ್ ಯು ಫಾರ್ ಲಿಸನಿಂಗ್.